The world of quantum physics, where imagination and reality cross lines that previously man had set for himself, opens the secret doors for new opportunities for technologies such as the use of quantum physics for communications faster than light. But as we navigate through such options, problems outlined by Einstein from over a century back that informs the laws of the universe, making it impossible for anything to travel at the speed of light, holds true. However, attempts have been made to utilize entanglement to go beyond this limit, and all the attempts proved that faster-than-light communication is still a dream. There is no better topic to discuss than the one that has mind-blowing elements that give insight into the nature of our universe. Quantum technology and research are bringing in new options such as faster ways of communication. Other forms of quantum communication are being investigated to be possible to go beyond the speed of light. In a principle formulated by Albert Einstein in 1905, it appears that nothing in space can match the speed of light. Wherever they are in the scale, the particles can only abide this limit as set by the principles of relativity while transmitting information across a given space. As to some concepts of utilizing curved space in order to signal these information carriers, they nevertheless cannot travel faster than light. Since the advent of quantum mechanics, people have endeavored to seek ways to finesse this rule through quantum entanglement. Many genius plans have been suggested to break relativity and send messages faster than light, since it remains merely as a theory. Thus, it is seen that using quantum entanglement, it is still impossible to have a communication which has a speed greater than the speed of light in our universe. Below are some examples that make attempts to explain the science behind this. Quantum entanglement is a concept that is quite different from what we can observe in our daily lives. Usually, if you toss your coin and get heads, it does not change the result of my coin toss. It still has the same probability of landing on heads or tails. This is because entangled particles have a correlation where measuring one can provide you with statistical clues about the other's state without actually deciding it immediately. In quantum physics, there's a phenomenon called quantum entanglement. It happens when you have two or more quantum particles, each with its own unique state, but together they share an important connection. It's like there's an invisible link between these particles. When we measure the state of one particle or coin, we can instantly learn something about the state of the other one, which goes beyond what we expect from normal randomness in everyday situations. Although it might seem like just a theory, scientists have been conducting experiments on quantum entanglement for many decades. They've created pairs of entangled particles, usually photons, and sent them far apart from each other. Then, using separate devices, they measure the quantum state of each particle almost at the same time. Afterward, they compare their results. These experiments are so significant that research in this area was awarded a share of the Nobel Prize in Physics in 2022. What we find, perhaps surprisingly, is that the results for your coin and my coin are correlated with one another. We've now separated two photons by distances of hundreds of kilometers before making those critical measurements and then measuring their quantum states within nanoseconds of one another. If one of those photons has spin +1, the other one's state can be predicted to about a 75% accuracy rather than the standard 50% you would have classically expected from knowing it's either +1 or -1. Moreover, that information about the other particle's spin can be known instantaneously rather than waiting for the other measurement apparatus to send us the results of that signal, which would take about a millisecond. It seems on the surface that we can know some information about what's going on at the other end of the entangled experiment, not only faster than light, but at least tens of thousands of times faster than the speed of light. Does this mean that information is actually being transmitted at speeds faster than the speed of light? If two particles are entangled, they have complementary wave function properties, and measuring one determines properties of the other. If you create two entangled particles or systems, however, and measure how one decays before the other decays, you should be able to test for whether time reversal symmetry is conserved or violated. If this setup worked, you really would be able to know whether the observer at the distant destination forced their entanglement pairs into either the +1 or the +- state simply by measuring your own particle pairs after the entanglement was broken from afar. In an easier quantum eraser experiment, scientists used two entangled particles that are separated and then measured independently. Surprisingly, changing one particle's state at its location doesn't affect the outcome of the other particle, no matter how far apart they are. This phenomenon challenges our classical understanding where actions on one object immediately affect another. In this experiment, particles such much as photons are fired through two slits, creating an interference pattern on a screen behind them. The interesting twist comes when researchers observe or avoid observing which path, which slit, each photon takes. When they observe, the interference pattern disappears, showing particles behave more like bullets. When they don't observe, the interference pattern reappears, suggesting wave-like behavior. Even if they destroy or retain this information after the photons have passed through the slits, it doesn't affect whether an interference pattern emerges on the screen. Unlike in classical physics, where you might predict outcomes given enough information, in the quantum world, uncertainty is fundamental. You cannot use quantum measurements to encode a preferred result. They always yield probabilistic outcomes. Even with quantum entanglement, you can't do better than random guessing when trying to know what's happening at the other end of an entanglement experiment. Whether it's about photon spins, flipping coins, or guessing the cards in a dealer's hand, the outcomes are fundamentally uncertain. Quantum physicist Chad Orzel explains that measuring a quantum particle is different from forcing a specific result, which changes its state before measurement. If you try to control the state of a quantum particle rather than just measuring it, you lose knowledge about the whole system as soon as you make that change. Quantum entanglement allows you to learn about one part of a quantum system by measuring the other part as long as they remain entangled. If it were possible to make exact copies of a quantum state, faster-than-light communication might be feasible, but this is also prohibited by the laws of physics. However, a theorem known as the no-cloning theorem, proven in the 1970s and 80s by different scientists, states that trying to measure a quantum state changes it fundamentally. This means you can't simply replicate or clone a quantum state. While quantum entanglement offers fascinating possibilities like creating secure lock-and-key systems that are nearly impossible to crack using classical methods, it doesn't allow for faster-than-light communication. The 2022 Nobel Prize in Physics recognized many aspects of quantum entanglement, highlighting its importance in research. In practical terms, quantum entanglement works in ways that aren't fully understood, but the main point is clear. No measurement can predict a specific outcome while keeping particles entangled. Quantum measurements always yield random results, ensuring that faster-than-light communication is impossible. This aligns with the idea that randomness is inherent in quantum mechanics, maintaining the integrity of causality in our universe. In the end of the video, quantum entanglement challenges our understanding of physics by showing us potential breakthroughs in communication and technology. It also highlights a fundamental rule: nothing can surpass the speed of light. Its mysteries and practical applications, quantum mechanics tell us that information transmission faster than light is impossible. This principle ensures the continuity of causality in our universe, maintaining its fundamental laws intact.